So today I will be doing number 10 for Rubicon 9A. So it reads, a proton is projected in the positive x direction into a region of uniform electric field E equals negative 5.50 times 10 to the fifth newtons per coulomb at t equals 0. The proton travels 7.3 centimeters as it comes to rest. So our gesture is a very bad drawing and I'm very sorry. But we have our uniform field here, positive side, negative side, and we know that in the electric field it is positive to negative, and we have a proton here, which is a positive ion, and it is going in the positive x direction this way. Unless you move. Boop, boop. So we have that, and the first question is determine the acceleration of the proton. So, and also, okay, magnitude, that means that it cannot be negative. So, I use the equation E equals Fe over Q, so electric equals the electric force over the charge. And we also know that F equals ma, F equals mass times acceleration. So, I did a little multiplication here to let it all be multiplied, just like made it easier. And then I replaced the FE here with this F, since F equals F, all that fun stuff. So MA equals QE is the final. Oh, sorry, oh my god, I'm gonna be kind of like going back a lot, just a warning. So this is an equation for the electric field. I don't know if I mentioned that before. So I have mass times acceleration equals charge times the electric field. Yes. Okay. And then because we want to just have acceleration, I'm going to isolate that. So divide by m, and I end up with the equation A equals QC over m. Now all I'm going to do is input what I know. So the charge, it's like not of an ion. No, I think a charge of a proton is typically 1.6 times 10 to the negative 19 coulombs times, and then from up here we have our negative 5.5 times 10 to the fifth. So, and then I put that in for the field here. So times negative 5.5 times 10 to the fifth newtons per coulomb, all over the mass of a proton, which is 1.67 times 10 to the negative 27th kilograms. So, multiply all that in, do all that, I'm gonna end up with negative 5.27 times 10 to the 13 meters per second squared. However, because it is magnitude, cannot be negative here, so it's just magnitude, so this is my final answer, and it will be in the negative x direction. If I can, I'm actually gonna get back to this one, because there's an explanation for it. Yeah. But we do know that it only works in the x in either the like x directions, because right here hold on, we'll get to that. Now the second part B asks determine the initial speed of the proton. I can do it again, but so because of that, I converted centimeters to meters. So 0.73 centimeters is 0.073 meters. So the final velocity will be 0 because it shoots off, bam, stops. And then our initial position is just gonna be 0. So I use the kinematic equation, final velocity squared equals initial velocity squared plus 2 times acceleration times the quantity of x final minus x, or no, sorry, x minus x initial. It will, I didn't like so now a minus because our acceleration is negative, and you'll see later, but no imaginary numbers. We don't want that. And also it just works out right. Just kind of disregard. So 0 equals initial velocity squared minus 2 times acceleration times position. I simplified that down even more, so now this is technically over here. Flip. So initial velocity squared equals 2 times acceleration times position, and then to get rid of that square there, I'm gonna take a square root of this, which is just initial velocity equals the square root of 2 times acceleration times position. Now I'm gonna plug everything in here. So we have square root of 2, obviously, and then the negative 5.27 times 10 to the 13 meters squared or meters per second squared. Oh, hold on, that's super embarrassing. Meters per second squared. Look at that. Imagine it never happened. Meters per second squared, which is the answer that we got for A up here. And then times 0.073 meters, and that's the computation that we did at the beginning here. Oops. Yeah. And then so I have the initial velocity after you do all that multiplication there. The initial velocity equals 2.77 times 10 to the 6 meters per second. This is going to be in the positive x direction because the projectile is initially shot to the right, which is positive, and so therefore acceleration it's an inverse relationship. So going back to this, that's why I kind of asked if I can get back to this. Be in the negative x direction. Did not mean to do that because negative x direction because it's an inverse relationship there. And so then part C, determine the time interval over which the proton comes to rest. So from when it's initially shot until it comes to rest, which also, I keep moving things, I don't mean to. Which also requires a kinematic here. So final velocity equals velocity plus acceleration times time. That looks better. Sorry. And then final velocity, as I showed in the previous one, is going to be 0, obviously. I have here, so it's going to be for this here, because the acceleration at that construct. So 0 equals initial velocity minus acceleration times time. We want time alone now. So time equals velocity over acceleration. So now plug all that in. We found velocity right down here. And then we found the acceleration here, right over here. So we plug all that stuff in, and it's going to be time equals 5.26 times 10 to the negative 8 seconds. So the reason I found this difficult was because, well, one, I was actually, this sounds so stupid, but I was kind of confused on the direction that I was going at first. And then I was thinking about it. So because it says I right over here, that means that it has to be in the x direction. Like the I hat, it's always in the x direction that way. And it literally says positive x direction. So that's super embarrassing. For like acceleration, I completely forgot about the relationship that I had. So, I direction at first, which was good. And then, yeah. I think what was really confusing is that BMC. Oh, I'm so sorry. I had to use my kinematics, and I wasn't really thinking of kinematics in this, so I was like, what is going on here? And then I was trying to find the one I lost it at first for some reason. Don't ask me why. Just no, it was super good. But yeah, that's the, like I said, the two kinematics that I used, I was like, can we use kinematics in E&M? That's more mechanics, but that's how I figured it out. Please tell me if I actually did that wrong, because I'll redo it if need be. That's it.